Okay, nice. Thanks. Let's do it. R of t. T. Cosine. We could actually draw this, see what's going on. You don't have to, but probably a good idea. We have basically here the path is a cosine. Bless you. Okay, so velocity at pi over 2, the velocity is going to be derivative of your position, 1 opposite of sine. Okay. And the velocity at pi over 2 is going to be 1. Sine of pi over 2 is 1, so we got -1. Our velocity vector here is 1, -1. It'll be right along the curve. It's tangent to the curve. Unfortunately, Liam, I took the very point where we got that problem with the normal vector changing from this way to this way. And I wish I hadn't taken that point, but what we're going to do is just swap the two, and we'll take the opposite of 1. But you have a choice here, and you don't know which way is inward. But fortunately, only one of the answers gave you the a unit tangent, a unit normal. So it works out. Okay, the speed, magnitude of velocity at this point, square root of 1 squared plus -1 squared, square root of 2. That's the speed of this particle traveling along this cosine curve. Number 3 is the acceleration, the derivative of velocity. And we want the acceleration of pi over 2. And we end up with 0, 0. No acceleration here. I know, it's a little weird. No acceleration at all. Okay? The 0 vector. Tangent vector. Take the velocity vector and divide by the speed. We could do this in general. This is what we got. 1 plus sine squared. That's the tangent vector in general in terms of t. To find the unit tangent at pi over 2, substitute in pi, we get 1, -1 over the square root of 2. So we get the same vector here, but made into a unit vector. Okay? Then, principal unit normal vector. At pi over 2, what we're going to do is take the tangent vector, swap these two, and take the opposite of one of them. Well, you do have a choice. You could go this way. When you're coming down here, these vectors are pointing inward, and when you hit here, it switches. Okay, so you can take the opposite of one of these, and the only one that gives you a unit vector here that's either this or this is D. So if you take the opposite of this, you're taking this vector here, the one pointing this way. And that's the answer that you need. Does anybody have, anybody got that one wrong? And Omar, what'd you do?
I used the thing where you do like the derivative of t over.
You tried doing that?
Yeah.
Ooh, wow, that's bleakness, because when you take the derivative of this,
I got 0 for both, and I was like, that's kind of.
You got 0 for both?
Yeah.
Well, that's probably what you should get. That's probably true. Wow, you did that whole thing?
Yeah, I did it twice.
I'm giving you credit for that, Omar. If you did that, you deserve credit. Where's? Oh, unfortunately, I don't have the scores here, so I can't give you any credit. Oh, no.
Well, I'm like a true politician.
Wait, what number are we on, Burns? Did we do 2 already?
Omar. Okay, I'm going to give you credit. Because that was an unfortunate choice on my part to pick that particular point where we have that particular problem. Yes?
Can we go back to 2? I was going over my physics test.
Oh, back to 2? Yeah, what do you need?
Partial credit.
Let me see.
See, Burns,
Go ahead.
I did this,
That's perfect.
and
Yeah,
then my
it's fine.
logic, yeah, but here's my logic. I was like, wait, x would equal 0 there, so it should just be 0. And I
Oh.
changed it last second,
Yeah. You're a human being, Teddy, you know?
and yeah, but
That's what humans
three,
do.
3 times in a row, Burns.
Yeah, you're a special human being. I give you credit on that. All right. Tangential component of accelerate. These questions again were weird. What's a tangential? You got 0 acceleration. Well, how much of the acceleration can you possibly have along the tangent line and along the normal line? 0. You can't have anything but 0 if the acceleration is 0. And when you do it out,
What?
Were these the weird answers you were getting yesterday?
No, I just like I was doing it, and it was just like D A A D D A A A, and it
Oh.
just seemed wrong. So.
well, what happens when you dot this with anything at all, the answer is going to be 0. So you get 0 along the tangent line and 0 along the normal line. So you get 2 zeros here.
Oh yeah, I did think that was kind of weird too. That freaked me.
That was kind of weird, but it's what it is.
It made sense though.
Yeah. You got those right?
Yeah.
Oh, good.
Luckily.
Good. And finally, the integral for the arc length. You're going to go from 0 to pi over 2. And what you're integrating here is the speed, the square root of. And we got the speed here. So, I didn't. Okay, it's the magnitude of the velocity. So it's the square root of 1 plus sine squared dt. That's how you do arc length, okay? All right. Everybody else sit on that? Yeah, Brennan.
For future reference for the tangent component and the normal component for acceleration, does it matter if you use the general form of acceleration dot t, like if you used 0 negative cosine t as
You could do that, but I wanted it at pi over 2, so at some point you're going to have to use the pi over 2, and which will give you the 0.
Afterward, it would still get the same.
Yeah, oh yeah, that'll be fine. That'll work. Yes?
So under what I put was, since before you make the sign positive, I had 1 minus sine squared t, and since that's cosine squared t, I got square root, I just got cosine t. Would that give me credit or?
Wait, where are you now?
So
What do you,
the arc length.
arc length. Oh, okay.
Yeah, so before you make the sign positive, you have, the derivative of cosine is negative cosine, right?
Derivative of cosine.
Negative sign.
Negative sign, yeah.
And 1 minus sine squared is cosine squared, right?
Correct. I can't argue with any of this. Go ahead.
So I got the square root of cosine squared, which is cosine.
Really? Now, there's a flaw in here somewhere, because that's now right.
They squared the
Yeah, you
sine
could be-
squared the square root, that's all.
Oh.
Yeah, but would you change the sign there before doing the trig identities, or?
Well, if you take sine squared and make it 1 minus cosine squared, you're not going to get cosine squared. You're going to get 2 minus cosine squared. There's no way that this will end up to be just plain cosine squared, unless you made some mistake along there somewhere. I'm not sure what happened in there. But here's the velocity. So what you're going to do for arc length is take the square root of 1 squared plus sine squared, which is this. Now, what did you do then? You did, tell me again what you did.
I stupidly
Well.
squared the sine and forgot that squaring the sine changes.
The sign to a plus. And then when you still had minus in here, so you had 1 minus sine squared, which is cosine squared squared. I'll give you half
That's
credit
when the
on that.
panic
I'll give you-
starts.
I'll give you-
Yeah.
That's a small math.
That's okay, Evan. Okay. That's a small matter. Okay. Of course, if you're designing a bridge and you do that, the first car that goes over your bridge, it's going to collapse. But other than that, it's a small matter. All right.
We're that great.
Other than that, it's fine.
Only partially your fault.
That's right. That's right. Okay, let's do the Bowman. Okay, we got the guy in a ditch somewhere. Yeah. Well, I had to do that so he fires the bow from ground level, so that we would eliminate that stupid H thing. Oh, then the people who took the test early had a slightly different version than the people who took it later, so they had an E answer in there, which, all right, so here we go. R of t, position anytime t. We've got v sub naught, cosine theta, t. We have a negative 1/2. Let's go for the general case first, plus v sub naught sine theta, t, plus h. Okay, that's a general formula, projectile motion. In this particular problem here, we're talking about meters per second, so g is going to be a 9.8. We already account for the negative in this negative 1/2 thing. V sub naught is 98 square root of 2. Angle theta is pi over 4. And h is equal to 0. Okay, so let's put all this information in to get 98 square roots of 2 cosine 1 over the square root of 2 t, negative 1/2 9.8 t squared plus 98 square roots of 2 1 over the square root of 2 t, and h is 0. Square roots of 2 cancel. Negative 4.9 square root of 2 cancel, 98t. This is what we have. That's our position at any time t. With this we can do everything. Time in flight. Set the y component equal to 0. Factor out a negative 4.9t. You get t minus 20 equals 0. Either t is 0, which we don't want, or t equals 20 seconds. That's the time in flight. Range. The range is where the thing lands. It's the x component at t equals 20. The range then would be 98 times 20, which would be 0, 16, 1960 meters, which I didn't have on the first test. The people took it early. For some reason, I vaguely remembered changing the problem around and forgetting to change that. Yeah, I know.
I'm like, oh my God.
I know.
Here goes everything for that section.
No, I know. I'm sorry about that too. Because generally I don't have any answer, but listen, Burns makes mistakes, on occasion. Right? On occasion I do. So. All right, but anyhow.
Sharp, so
yeah.
There's proof.
Time to reach max height. Well, the easiest way in this problem, if you're launching from 0 height, the time to reach max height is midway between the two. You got 0 time here, you got 20 seconds here. It's going to be 10 seconds. So the time to reach max height is 10 seconds. Okay, that's going to be 10 seconds. Okay. What is the max height? Well, at 10 seconds, find the y component at 10 seconds. So the max height is negative 4.9, and we've got 10 squared here, 98 times 10. That's 100 times this. That's a negative 490 plus 980, and you get 490 meters. That's max height. The x component of the velocity at max height. Well, the velocity is the derivative of the position, and that's 98, and that would be a negative 9.8t plus 98. Okay, and we want the x component at max height. Well, it's 98. The x component of velocity is always 98. Okay, that doesn't change. The y component, which does change, okay, is a negative 9.8 times the 10 plus 98. That's equal to a negative 98 plus a positive 98 is 0. And that's what you would expect at max height. The y component of velocity is 0. Okay? So y component of velocity. What's that?
Those are math questions. Those are physics questions.
Yeah, you could make that argument, Liam. That's true. That is true. And that's that. Okay? Everybody all set on that? Good deal. Wow, we're rolling along here. This is good. So, Last part. Last part is on vector value function of 3 space. Rather lame-o one, but what are you going to do? T, T, T. Okay. What do we have here? We have a line in space, okay, starting at 0, 0, 0, and heading up this direction. Okay, where the x, y, and z, all those components are the same. We got that line. So, what do we have to do? Velocity. 1, 1, 1. It doesn't matter what time, because it's a constant 1, 1, 1. Acceleration. Take the derivative of velocity. 0, we got no acceleration. Okay, it means we have a constant velocity. Speed. Well, if we got a constant velocity, it doesn't matter when we do the speed. It's the square root of 1 squared plus 1 squared plus 1 squared. It's the square root of 3. Okay. Unit tangent vector. Unit tangent is equal.
I got a.
Oh, what? Okay, go ahead.
Credit here.
Oh, you do?
You see, I actually did that, got the square root of 3, then some genius, came through the second time and figured, I'm not going to do any work and just say it's 3 because, I don't know. I don't know what
That's a
wrong
good
there is.
explanation. Yeah, okay.
It hurts. It's
You
You
got
gotta
it.
watch out for the other genius, man.
it's painful, Burns.
Whoa, you got square root right there.
I did. I wrote it right there, circled it right here. Then I was looking over my test and did it over in my head and was
Wow.
like, definitely 3.
Alrighty. Unit tangent. We need R prime over the magnitude. Okay. So unit tangent vector is 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. That's the unit tangent vector no matter where we are. Okay? No matter where we are. Arc length. Square root of 3 dt. Square root of 3 t. Square root of 3. Arc length is, I don't know, yeah, problem was not that complicated. And then curvature, kappa, magnitude of t prime over the magnitude of r prime. Well, geez, if t is this, t prime is 0. And if we have a straight line, which you hopefully recognize that as a straight line, the kappa's got to be 0. Okay?
There are no water creatures within the vicinity.
Teddy.
I got another one. I did it again. Actually, this one I kind of did really get wrong, but I did the. All right, so I did this. I did the r prime over t prime, then got that, and then I was like, maybe it's not t prime. So I went back and did it and got that.
Can't do it, Teddy. Sorry.
Can't?
No. You messed up the formula.
That one really hurt too.
Yeah.
Because it was just such a dumb mistake.
Well, that one, the other ones were dumb mistakes. This one was not knowing the formula.
Those ones weren't even mistakes though. They were just. I literally don't even know what to call that.
Dude, you gotta watch out for Teddy's doppelganger.
Yeah, I mean, I was just doing great and then drove off the side of a cliff.
Oh, well. You didn't do badly on the test, Ed. It's not like you got a 20 or something on the thing.
Yeah.
It's not like you got a 46.5.
Yeah, that would be awful.
Yeah, that might as well blame it on the teacher.
Yeah, that's true. All right, so here we go. You guys ready? Moving on.
Wait, actually, I had a question.
Oh, go ahead.
So, maybe it's just an issue with my list.
Oh, you were asking me about the plane. Oh, no, somebody was asking me about, Omar. Okay. All right, well, I'm
Well,
going to
if
do
you want
that.
to do one more first or whatever.
Oh, go ahead.
So this is how I define my thing. I got the R of T.
Yeah, you're gonna have a problem right there, because people, when you're doing the lab on this thing, you're way better off doing an Rx of T, an X position, an X component, separate from a Y component. You can't define that vector value function as that.
So defining R of X
Rx of t
Rx.
equals the x component, and Ry of t equals a y component.
Oh, so
And
you
then
just-
you want to do each, yeah, keep the components separate.
And then if I do that, should this list stay the same? No.
That list is not going to be good there, Dean. You want to do a table of errors from 0 to 0, and you want to go to x of t and y of t. That's what you want to do for your arrows, x of t and y of t. The problem is you got 3 components here, and over 2 here. Mathematics says, what the heck are you trying to do? Okay. Then what you want to do when you do the velocity vectors,
Oh, this is defining the x versus the y component.
yeah, this is the vector value function. This is giving you the function itself. Path, okay? That's what this one is. And you want to do that 0, 0 to your x of t and your y of t. Keep them separate. Yeah, you're going to have to redefine x of t and y of t. Do it, yeah, here, yeah, do it that way. Instead of rx of t, I would recommend x of t. I think this is the way I did it. What was the, what 4 cosine, 2 sine, or something like that?
Yeah.
Okay. You want 4, capital Y. And you want y of t. Keep them separate. Like 2 sine of t.
Oh, okay.
And then when you do your table of values, your arrows, you want to go from 0, 0 to x of t, y of t. That's what you want to do for your arrows. And then plot those.
Okay, so then I define the b of t and the a of t separately like that.
Yes, yes. Do your x component and y components. Keep them separate. Keep them separate. Now, I don't know how Dan did it, but that's the way I recommend you guys do it. Okay, Dan, I don't know how you did it. Did you keep them separate? No. Okay, of course not. All right, that's okay, Dan. But I recommend you keep them separate. Okay, and that's the way to do it. Okay. He did it as a vector, the whole thing as a vector, and did it all at once. But I think you're going to be better off with what I said.
You need to pay attention to a couple of obscure things in arrow if you want to keep them together.
Yeah, yeah. There's a few little things that easily messed up on. But I think if you keep them separate, I think you'll be all set. Okay. We had another question. Go ahead.
So for the plane 4x plus 8y plus 12z equals 12,
Ooh, this looks familiar. Bless you. Go ahead.
find the coordinates p, q, and r, and then find the cross product of vector p, q. with that.
Okay. Find 3 point. Yeah, we did this. Where were you, Homer? Remember we did this? Okay, we want to find 3 points, P, Q, and R. And probably the easiest to do here are find the intercepts, okay? In other words, let y be 0 and z be 0, so x is 3. So let's say point P is 3, 0, 0. Okay? And then what we want to do is let y be 0 and x be 0 and find z to be 1. Oh, okay, well, I did it. So 0, 0, 1. In R, okay, we'll find the y by letting x equal 0 and z equal 0. So the y would be equal to 12 eighths, okay? We got 3 halves.
Usually they're not going to lie in order of X, Y, and Z for P, Q, and R.
Yeah, that would be best. See, I saw, as soon as I did this Q, I thought, I should have done it that way. I know. I did it. So,
Pearson software.
here we go. So you got 3 points. There's an infinite number of possibilities there. But they want you to do PQ, which would be, see ya. PQ. What? Was that it? Was that? Well, she's going on a trip. She's going away for a while. So, anyhow, all right, PQ. So PQ is negative 3, 0, 1. PR is going to be negative 3, 3 halves, 0. I don't know if I did this in class or I did it with one person in particular. I was talking. Did I do this in class? Or was I talking to one person in my office? Bless you. I don't know. I can't remember. But anyhow, so you have this. And then they want you to cross these two vectors. Okay? When you cross these two vectors, what happens is you get a vector orthogonal or normal to each of these. That's the vector that's normal to this plane. But we already know the normal vector to this plane. The normal vector to this plane is 4, 8, 12. So when I cross these two, I'm going to get a vector that's going to be a constant multiple of these. Okay? That must be the case. And you can see it. Let's just do this. And then I'm going to start the next chapter. We'll just get started on that. Okay? I, J, K. Okay. -3, 0, 1. And -3, 3 halves, 0. Okay? So what I'm going to get here is a vector. Cross this out, it'll be 0 minus 3 halves. Cross this out, it'll be 0 minus -3, which is 3, but it's the middle guy, so take the opposite of it. Cross this out. And then I'm going to get -9 halves minus 0, I think. If I do that all right. Now, watch this. If I take out a -2, what I'm going to get, a -1/2 is really what I want to take out. I'm going to get a 3, 6, 9. That's not what I really wanted. I want to get a 4, 8, 12. Well, okay. Yeah, I know. I can do it by, if I take a 3 out, now I'm going to get 1, 2, 3, and then multiply by 4 to get 4, 8, 12. It'll come out. So what I'm going to do is multiply this by 4/3. Okay, watch this. If I multiply this by 4/3, I am going to get -1/2. 3's cancel. 4, 8, 4, 8, 12. Sorry. I'm sorry. The point is, no matter what points I take, and there are infinite number of points, and then what two vectors I select, when I do the cross, I will always end up with a vector that's a constant multiple of this normal vector, because that cross product is a normal vector to the plane. Okay? And there it is. All right? Thank you, Dylan. Thank you, Dylan. Thank you. And it works. So that's what you're going to get. So if you don't even do the cross, but just put in 4, 8, 12, you're going to get it right.
Oh, really?
Yes. Trust me. You trust me on that?
Yeah, I do.
We can still put in answers on older web signs.
Yeah. No. Wait. Oh, there's due dates for those, huh? Yeah, there are due dates for this.
There was one I missed. Or not one, but
Email
there was
me.
two.
I'll change it.
Yeah.
Email me. You can email. Anybody, email me if you have WebAssign that you missed first time around. Send me an email and say, Burns, I need you to change this so I can do this, okay? We can do that.
What about like labs?
Labs are a little different, but send them in. I'm not gonna give you 20s and 40s. I'll give you something. Yeah, I'll give you something. All right. Let's move on. We got a little bit of time here. We got to move on some. Here's what we're doing: functions of two variables. This is chapter 13.
Yeah.
This is where we are. Wow.
More vectors?
No, actually not.
What is this, critical points and stuff?
Critical points, yeah. Max min problems at the end. This is some good stuff here. Nice stuff. Some good problems. Chapter 13. This is functions of two variables. Oh, this chapter is going to take us a while. All right, this will do a long chapter.
Watch out.
Ooh, long. Functions of two variables.
Is it still in 3 space?
Yeah, we're definitely going to be in 3 space. A function of two variables will be defined this way: f of x, y. Let's take let's take f of x, y, and this could be written this way or this way. You know, when you have functions in 2 space, you can either write y as a function of x, y equals something, or you can write f of x equals something, function notation. Same thing here. You can either use z and have x's and y's here, or a function of x and y, okay? What is a function in two variables, Stu? What it does is takes an element from the domain. Now, what's the domain of a function of two variables? The domain consists of all the ordered pairs for which the function is defined. Okay? All the ordered pairs now. What's the domain of a function of a single variable? It's all those real numbers along the x-axis for which the function is defined. The domain of a function of two variables would be all those ordered pairs now for which the function is defined. What's the domain of this function here? What are the possible ordered pairs?
All real.
Yeah, all reals. Okay, x and y both all reals. What's the range of this function?
All positive.
Oh, yeah, you can't say positive. You have to say, yeah, 0 to infinity works. All non-negative, okay? Because 0 is neither positive nor negative. So you have to say non-negative if you want to be entirely correct, okay? That's the range of this function.
Is that one of your crazy Z's or is that a Y?
That's a z. That's a z. It's not a crazy z. It's a regular z there, David. All right?
See, other people are having fun with it too.
Yeah, I can see that.
I actually put
Teddy.
1023, right at the top of the paper.
Let's do it.
Oh, I didn't even see the alpha.
Is that alpha or an X? Is that alpha?
What are you saying? What are you guys doing? That's an x. That's an x. That's an x.
It's alpha. What?
It's an
See what I mean? See what I mean?
Yeah, I can see the alpha.
I wrote
yeah.
I can see it too. It's an x. It's an
I'm seeing
x.
extra Y's and alphas all
Oh.
over. This is going to be a
All right. All right. So for this function of two variables, domain consists of all ordered pairs in the xy plane, x and y, any real number, but the range is the non-negative real numbers. What does a function of two variables do? It takes an ordered pair in its domain and assigns it a value to its range. That range, the z function, that z value. So what do we have here? We have taking all these ordered pairs in the xy plane. What does this function do? It assigns them to a value z. When we take all those things, we'll have a three-dimensional surface. Okay, we'll get a surface. Generally speaking, functions of two variables define surfaces. Okay. Now, what will this surface look like? Well, there's a couple ways to do this. One way to get an idea of what the surface looks like is to do what are called level curves. Okay, and that's what we're going to do here. We're going to do level curves. Level curves are the intersections of our surface with planes parallel to the xy plane. Okay? What's that?
Say that again.
Okay. Level curves are the intersections of our surface with planes parallel to the xy plane.
This is going to get crazy.
Nah, it's not that bad. So, let's do some level curves here. Let's start, and what WebAssign will do is say, let's let c equal 1. Let's set c equal 0 first. And what that means is replace the function here with a constant 0. So you get 0 equals x squared plus y squared. Okay? What we're doing here by doing this is finding the intersection of our surface with the xy plane. The xy plane has an equation of z equals 0. We're letting z equal 0. We're finding the intersection of our surface with the xy plane. What do we get? What ordered pairs do we get when 0 is equal to x squared plus y squared? 0, 0. We get one single point. Okay? Now, here's what I'm going to do. Here's my three-dimensional surface, but here I'm going to put my level curves. Okay? 0, 0 is what I get when I let c equal 0. Now let's let c equals 1. What I'm doing is taking our surface and intersecting it with the plane z equals 1. What do we get for an intersection of our surface with that plane? More than that. What do we get? We get these.
We won't fold.
What does that describe? X squared plus y squared equals 1? A circle, a unit circle. we'll get these. We'll get this, a unit circle. Okay? We'll get a unit circle. Let's let c equal 2. We'll get 2 equals x squared plus y squared. What does that describe? Another circle. Okay? Circle radius square root of 2. Whoa. All right? And what we'll get for our level curves is this. Okay? That's what we get. Point, circle, or unit circle, bigger circle, bigger circle. This is like if anybody does orienteering or anything like that, when you got a topographical map, what it does, the level curves connect points of equal elevation. And if you're going to climb a mountain, you go to Greylock or something like that, you're going to see these lines that connect points of equal elevation. What happens when you get something that rises steeply? These lines are very close to each other. Because what do? They do lines of increments of like 50 feet or 100 feet elevation. So if you got lines that are very close together, that tells you you've got a steep rise. Okay? You got a steep rise. Topographical maps will do that. If you look at a weather map, they'll connect points of equal barometric pressure. Isobars are called. Okay? And the isobars will connect points of equal barometric pressure. And you can define fronts, warm fronts and cold fronts by doing that. Isotherms, you got lines of equal temperature. You got the same kind of an idea. Okay? Now, what is this? How does this translate into our surface? Well, our surface is going to look like this. Okay? Etc. It's a paraboloid, okay, and it comes up this way. It's a bowl. Our level surfaces are these circles of these intersections of our surface with those planes pushed down to the xy plane. Okay? All right, well, we'll start there. And then what we'll do on Monday, we'll continue with this, and then we'll do some limit problems. And you can imagine limits in 2 space are one thing, but limits in 3 space, entirely different. So we'll do that. Keep on going. Yes, Timmy.
I don't want to ask this.
You do that. We can do that. All right.
I want to go to the
How long are you going to be?
Yeah, go ahead.
That's got to get us. Like, what if you guys said, what was on the way that happened? And it happened. You can predict the future. I mean, I'm still shocked about it. I'll try to figure it out. You're my fortune advisor. I'll try to predict the higher vectors. Next time, could you maybe get into like the 70s, low 80s? I mean, I'm not asking. That's like MIT. I mean, I think you have to go back. Because I don't want to go to the math physics. You want to start like so. I have to let you start. Oh, yeah. Take the over. Because I had like this was okay.
Yeah, that is you put
yeah, I'll check soon on my way out.
I'll start x of t, y, yes. Because, well, you got your position vectors that give you the path. But then what's your acceleration at this point along the path? And your velocity is at that point on the path itself. So you got to start there. And then you,
So this is like position.
that's your position.
So the reason why it's there is because it's going to be changing over
Yes.
time.
And then what you want to add to the x of t for your second point is x of t plus, for example, the velocity x prime of t.
And then this one, I'm going to be creating two more functions. T is equal to the x function for tangent vector, and then g of t.
It's like I'm just like so stressed out every day. Now. Like it doesn't matter. It's Friday anymore.
Okay.
And then make it x of t plus f of t, and then g of t plus
Y of t plus g of t.
or y of t plus g of t. Okay.
Absolutely.
Alright, I just want to make sure on that.
Yep.
Should I follow you?
What's that?
Should I follow you? Because I found that I don't know what's wrong with me.
What's wrong with you?
Yeah, but
I don't know, Gideon. I hope it's not serious.
I must have like a serious mental problem. So this one you saw it, right?
I saw something here. Did I give you credit?
No.
No, I didn't. I said no, Gideon.
You said no.
I said not you?
Yeah.
He said that to you?
Say that to me.
Gideon. Oh, you're right. There's no function there.
You broke my theory.
Oh, man, I'm
Same with
sorry.
this one. I mean, I did the scratch work, like my work for.
That's still recording.
Yeah,
cool.
I mean,